Hi everyone, I'm Radoslav and I'm going to be talking about the shrines problem, which was from the April Long challenge. It was about some quite complicated concept, but it kind of required one part which was ad hoc. And to be completely fair, even without reading a lot of literature, there was a way to come up with the whole solution. So in a way, it was a pretty cool problem. And without further ado, I'm going to start with the problem statement, and then I'm going to basically describe how the solution will go. So I'm going to keep the problem statement explanation quite brief because in general this problem was basically the hardest problem in the contest, and I don't think there is a lot of sense in basically just going through the problem statement. So a very brief overview. So you have two endpoints on a circle, and after that basically you have some segments which are given to you, which connect 2 points, like 2 points on that circle, basically like endpoints, one of those to n. And what you do is, in a way, you build this graph which contains the first two endpoints, and also it contains all the intersections. So in other words, here we have an edge between 1 and 4, between 2 and 6, and this actually creates this additional vertex 10, which is the intersection. So in other words, you initially have this circle which has two endpoints, and after that you're given some edges, and you also add the edges which are like intersections. You also add the vertices which are basically intersections of two edges. And the thing is that now that you actually have those new vertices which are in the middle of some edges, we are going to consider the edges as being the smaller part of the whole edge. So in other words, like in this sample, after we have intersected all edges, we are going to have fewer, we are going to have shorter edges in some sense. Like now 6 to 1 really be an edge. We are actually going to have two edges, which are from 6 to 10 and from 10 to 2. And yeah, basically we have this weird construction which actually turns out to be it is a concept which has been researched, but yeah, you have a graph which is given in this form, but also we have those constraints which are, more specifically, there is this constraint which is when we look at the segments, then no three segments will actually intersect at one point. So this is the first thing. I actually wanted to highlight the other one, but the previous one is also kind of important. So the main constraint for this graph is that when we get three segments, they can't pairwise intersect each other. So in other words, you can't really have a triangle in the initial graph. So if we had an additional edge which was basically like that, if you can see my cursor, so it was it kind of crossed two of them, this would have been impossible. So in other words, you can't really have triangles in this graph. But yeah, let's go back to our problem. This is pretty important constraint which is kind of used in the solution. And yeah, now you have this graph, and this is kind of a spoiler, but I guess everyone who thought about the problem realized that this graph is planar because we get all of the intersections and we explicitly make them as new vertices. And now what you do is you look at the regions, which are basically in a way, when you have a planar graph, you have faces, and we call those faces regions. And we are going to create a new graph such that the vertices in this new graph are basically the faces. So in other words, those new vertices will be 1, 2, 3, 4, 5, 6, and 7 in this example. And we are going to connect two regions when they have basically a common edge between them. So yeah, this way we create this new graph, which is quite weird, and we are basically selecting, this is basically those are the regions, and we are selecting a set of vertices which are, in a way, in the problem statement it's said that k of those regions are chosen by some gods, and yeah, we are gonna say that those cities are basically chosen by gods. And now we have like this final definition, which is holy cities. And holy cities are cities that minimize the sum, which is basically the inverse of the sum of the distances um, from like some vertex to basically everything else. In other words, what this means is in a way like some S vertices are chosen, which are like the chosen by, I mean, K vertices are chosen by gods, and this is like our set S. And now we define a holy vertex as a vertex that maximizes this sum, but like this inverse sum. But the thing is that this means that in a way, the holy vertices are in the middle of all of the chosen vertices. I guess like if you think about it for some time, you kind of need to build some intuition for this problem, and you can't really do this in a video editorial. But yeah, in a way, like some S vertices are chosen, and the holy vertices are defined as the vertices that minimize the sum of the distances. And yeah, I mean, this is basically the start of the problem. And now the thing is that I cannot explain the setup, but we actually don't know which are those S vertices. And we're interested in the holy cities, but like we don't really know which are the S cities. Because if we did know them, we could have like somehow constructed the whole graph, and then basically just with brute force, we could have found like basically the distances between every two pair of vertices, and after that we just find the holy cities. However, we don't know S, like the set of the chosen vertices. But something we do know is that we can ask a question or like a query, because this problem actually was interactive. And the query is basically we are given two vertices, U and V. And in a way, what this query represents is that it looks through all vertices in S, and it tells us the number of so because we are given like for the query two vertices, it basically returns the number of vertices which are closer to U than V. In a way, like you can imagine that you give it two vertices and you kind of like hold two parties or something in those two cities, and every person from like those chosen by God cities will go to either of the parties, but he will go to the shortest, the party which is closer. And this way, what happens is that you're gonna get like the number of people who are gonna go to the first party and the number of people who will go to the second party. So all in all, I think this kind of explains the problem statement. But I think it's just like a great idea if you kind of stop the video, you read it through and like try to understand it, because yeah, it's a bit hard to basically get the solution and everything if you haven't properly understood the problem statement. But yeah, I mean, that's pretty much like the problem statement. And yeah, we can call this query at most C times, where C is the number of regions. By regions, I meant like the faces of this graph. And yeah, I mean, you can see that the constraints aren't very large. They're like up to 300. And yeah, that's pretty much the problem. So the last thing I need to mention is that we are basically not given, so normally when you have a planar graph, you would be given like either some points, or yeah, you would need to notice that the structure is basically a planar graph. But in our case, we are simply given, yeah, basically like the points. Here we are given 1, 10, 2, 3, and we are also given the edges. But the edges aren't given in the way, we aren't basically given the circle edges, but we are given like those small edges. In a way, we are basically just given the whole planar graph structure, and we kind of need to find the faces. And yeah, I mean, finding faces in a planar graph can be done, but it's like a pretty hard task. So that's why we know that the graph is basically cyclic. But yeah, I mean, without further ado, let me just go straight to the slides, because yeah, I do have some slides prepared. All right, so basically, again, actually, what we are given is a circle graph. And the circle graph is defined as a planar graph, which is basically created by intersecting the chords of some, yeah, basically like intersecting some chords. And yeah, I mean, it's actually kind of studied, and there are, if you look for this literature, there are algorithms which basically just construct the faces. However, you can also try and figure out an ad hoc construction for this. And yeah, I mean, I like the ad hoc construction here more because it's like, it's, if you actually think about it and how you would build the faces, it's not that hard to come up with something that would work. And here I'm going to present the way the author like intended for the construction to happen. And yeah, I mean, we are going to be constructing it with a BFS. In a way, we also will be having like some open and some closed faces. And I'm going to explain what this actually means. So basically, an open face would be some face that we have kind of opened from the side of the circle. In other words, like we still haven't completely closed this face. And what we are going to try to do, initially we're going to have like a lot of very small open faces, which will be basically on the surface of the circle. And what we are going to try to do is to kind of like make the circle smaller. Basically, it will kind of change its shape, but we are always going to keep like a set of some open faces, which will represent not really a circle, but something like circlic in a way. And yeah, we are going to try to make this thing smaller and smaller until we have something very small, which doesn't have any edges inside of it. And we will, or all of like those will be parts of an open face, and we are going to kind of combine all of these small open faces into the final closed face. But yeah, I mean, let's just go straight into how we are going to do the construction, because I feel like if you actually see the construction, like the whole algorithm, it's way easier to see why it works. So initially, we're going to have like two n open faces. And the open faces are basically going to be those arcs which are between two consecutive points on in our graph. In a way, like it's going to be like between 1 and 2, 2 and 3, and so on until like 2n minus 1 to n, and finally 2n 1. So in a way, like as I said, we have initially the whole circle as some small arcs or some small open faces between consecutive vertices. And yeah, now we basically just need to figure out what the rules are so that we can actually do this BFS, which from like the whole circle kind of like makes it smaller and smaller. And yeah, let's go to the first rule, which is actually pretty simple, I would say. So consider like two open faces, which are like from, like their endpoints are L and M, and the other one is M to R. And in the case, they actually don't have any outgoing edges or like any connected edges, apart from like, I mean, they don't have any outgoing edges that we haven't like visited yet. So in other words, like if basically we have like just two consecutive things which are connected and we can't really extend them further, we can basically easily just merge them into something new, which is like basically with this middle point. So in a way, like if we have two open faces which don't have outgoing edges, we just merge them. This is quite obvious because if you can't really extend or close those faces and they're adjacent, you can easily just merge them. So yeah, this is like the first thing. And then the second one is like, in the case that we actually have some open faces, which are like L to R, well, like basically like if we have some open face, which with the endpoints being L and R, and there are like some other things in between, then if we have some new vertex which is connected to both L and R, what will happen is that this will actually close the whole face, because in a way you are going to have some new vertex which is further closer to the center of the circle in a way, and it will basically just close the current LR. Yeah, I mean, LR was an open face. If you just have a vertex which is connected to both of the endpoints, you can close this edge. However, this means that you also need to add two open faces. And those two open faces would be, if the vertex was V, there will be L to V and R to V, or like V to R, depending on how you implement it. But yeah, I mean, in a way, like you close this face and you create two new faces. So this is like the first case. And actually, the second case, like the last case, is pretty much a generalization of the previous case. But in the case that we actually don't have, I mean, in a way, it can happen that there is an edge between two vertices which are fully inside of some face. In a way, like if we have some face, which is, by this definition, I mean like it's a vector, and at some point there are like basically some vertex A and some vertex B, and they have like an edge between them. So this means that this will close the edge which is from A to B, and it will also create a new face which is from L to A to B to R. So in a way, like this is pretty much like removing some segment from like the open face, and then also creating a new closed face, which is basically A, the things between A and B, and yeah, basically just this subsegment, and this is closed. And you can prove that if you follow these three rules, you're gonna end up with like a very small circle, which is pretty much like with no edges inside of it. And this will mean actually that yeah, you're gonna have like this final face, which is in the middle. But yeah, I mean, this construction is pretty cool. You can like try to think about it a bit more, but yeah, it can be implemented in various complexities. But the constraints were pretty low, so even a cubic solution would have passed. Because like, I mean, this is trivially can be implemented in cubic time. I think it's also relatively easy to implement it in quadratic time. So yeah, you can easily implement this part. So basically, to recap, what we are going to have after this point is that we're going to have like this, basically like the graph of the faces. Because, I mean, I think the author initially, I think the problem was you were actually given the phase graph, like the graph of the phases, and it was just the interactive part. But actually this construction is, in my opinion, pretty interesting, and I think the author thought the same, so he decided to like include it in the problem. And yeah, I think it's a pretty cool thing. But yeah, now let's actually go to our problem, which is how to find the holy vertices. And to remind you, the holy vertices were basically like, in a way, the vertices which are closer to, well, the holy vertices are those vertices which minimize the sum of the distances. And yeah, like the main idea is that there is this definition, which is like a median graph, and it's actually pretty simple. Like for all median graphs, if you have three vertices A, B, and C, then whenever we have some, basically like if we have three vertices and we consider the shortest path between all three of them, then there is like a unique path, unique vertex, which is kind of in the middle of them. Or in other words, like there's a unique middle vertex, which we can define by MABC, such that the sum of the distances between C and MABC, yeah, I mean, basically like it's basically like for every three vertices in a median graph, then this vertex which minimizes the distances between all of them is basically unique. And yeah, like obviously one example for median graphs is trees, because yeah, I mean, yeah, it's quite clear that if the median vertex would be, if you root the tree at, let's say, A, it would just be the LCA of B and C. But yeah, I mean, I guess you can figure out that it will turn out that our graph is actually a median graph, and this happens because I think I already mentioned in the beginning of basically like the video, that's the constraint that basically no three lines pairwise intersect each other is very important. And this is important because this basically means that the graph which is given to us in our statement is actually triangle free. And there's like this, I mean, it's basically like, it can be shown that if you have a triangle free planar graph, which is on a circle, but I think it also works for any planar graph, then if it's triangle free, then it's also like a median graph, which is actually very interesting because for median graphs, they're nice. I mean, for median graphs, you know this uniqueness constraint, which means that it's actually like when you get two vertices, that there's a unique direction in which you know basically like this middle vertex would be. But yeah, I mean, but basically because of our constraint, we know that our graph is median, so we can actually solve the whole problem. Again, this is like just an overview of the whole solution. If you're interested in it, you can go to the editorial, which has like a slightly more formal and like a longer explanation of the whole thing. But yeah, basically like the first part is the ad hoc construction, which we already kind of explained. Then after that, we actually have the interesting part, which is, I mean, I feel like most people who actually reach to this part would have some guess on how to do the whole solution. Because, yeah, in a way, you can see that our query kind of gives us two numbers. And if you actually figure out that our graph is basically a median one, then if you have like those two vertices, then we know that there's a unique direction in which our holy vertex would be. And yeah, one easy way to do this is to basically just like use the majority strategy, which is like we start from just any arbitrary vertex, and we try like let's say I mean like we basically try all edges, and if there's an edge where at least half of the basically like if there's some edge from our arbitrary vertex which has at least half of the vertices closer to that. I mean, okay, if this edge was UV, then if V was a better choice, we can say something is a better choice simply when like more parties happen in, more people go to the party in this other vertex. So this basically means that if we have such an edge, we can basically just replace U by this vertex and we can continue our procedure. And the interesting thing happens here because we actually know that from U, there will be exactly one edge with such a constraint. So, I mean, this kind of uniquely defines our path. And at some point, we are going to know that all of the vertices reachable from U are at least as good as, I mean, but basically they're either as good as U or they'll be like worse than V. And at this point, because we are actually asked about all of the vertices that minimize the distance, what we do is we can do something like a BFS or something similar, which would basically like just start from our one vertex which we know is holy, and it can go like to the other ones, and we know that there will be like adjacent to it. So yeah, I mean, maybe it's a bit complicated. Also, you have to kind of like implement it nicely because you have this limit of basically like C queries, and you don't really want to overcount any vertex. But in general, like the number of queries can be done so that it will be less than the number of faces, because you don't really want to ask more than one query about a vertex. Because like if you have already, I mean, so you start from some vertex U, and if you move to some other vertex V, and you have realized that this V isn't an optimal choice, you can just say that you are never going to ask again for this vertex V, because it's a non-optimal move to actually go to this vertex V. Because, yeah, I mean, if you don't really get a majority for some V, this means that this V will never actually be a holy vertex. Otherwise, you kind of like just go to this V and you continue our procedure. And it can be shown that you're going to ask for, I mean, you can easily implement this so that you ask for every vertex at most once. And this actually leads to, in the worst case, C-1 queries, which is less than C, which was our constraint. But yeah, I mean, that's pretty much the problem. It's quite complicated, so I wanted to keep the whole explanation quite short. And most people who are actually interested in it can look for the solutions or the discussions. And yeah, I think it was pretty cool, especially the construction, because it's like an ad hoc thing. And yeah, I mean, it's quite interesting to solve it without going through the literature. But if you actually went through the literature, most likely you would have noticed the fact that a triangle-free circle graph has its dual graph of faces, or being a median graph. I mean, it's not stated in such a way, but if you look through the algorithms, you can kind of like find this fact, and after that, the problem doesn't it becomes like way simpler. And yeah, I guess like the main intuition would be to, when you realize that it's in a way like you can, when you choose two vertices, you can basically do this like local search like approach, which is like basically the majority approach. Mostly because like it's kind of similar to trying to find the centroid in a tree, and if you think like in this direction, I feel like it shouldn't be too hard to come up with the whole solution. But yeah, I mean, that's pretty much the problem. I think very few people solved it. I think around 10, and yeah, overall I think it was a pretty cool problem for a long contest, because you have like a lot of time and you can learn some new things or idea. So yeah, I hope you enjoyed, and I guess see you next time.